Hypothalamus artificial intelligence, HI. Digital transformation powered by autonomous and intelligent algorithms in real time. Presents its solutions based on artificial intelligence for decision-making for mathematical models for enterprise-wide optimization in process industries. Case, oil refining. HI has the support of its technological allies, General Algebraic Modeling System, GAMS, and IBM, producer of C-Plex Optimization Studio. Both products are incorporated into HI's artificial intelligence solutions. Enterprise-wide optimization in process industries. The offer presented by HI is based on the vision of the so-called enterprise-wide optimization, EWO, that is an emerging area that sits at the interface of industrial processes and intensive operations research. Due to the advent of Industry 4.0, it has become a major target in process industries due to the pressures to remain competitive in the global market. EWO involves optimizing a company's core operations, sourcing, manufacturing, distribution, and financial activities, to maximize its economic utility from a holistic point of view, and not through separate silos, with weak connectivity between them. This, coupled with global pressure for sustainable industries that have environmental aspects in mind, such as the clean production of the energy they consume. One of the key features of EWO will be the integration of information and decision-making between the various functions that make up an industrial supply chain. This can be achieved with modern computing tools, cloud and edge computing, which together with the Internet of Things, IoT, have promoted e-commerce. To fully realize the potential of EWO, the development of sophisticated optimization models and algorithms, analytical IT tools, is needed for optimal overall economic performance, as well as high levels of customer satisfaction. An additional challenge is integrated and coordinated decision-making between the various functions of a company: purchasing, manufacturing, distribution, sales, human resources, maintenance, energy management, etc., across several geographically distributed organizations, suppliers, facilities, markets, etc., and across various levels of decision-making: strategic, tactical, and operational. HI's vision, developed in practice over more than 35 years, has allowed HI to evolve from decision support systems, conceived as the chaining of algebraic equations, to the chaining of pre-formulated problems, to build a super decision-making system, as a Lego game. Under this vision, it has developed the proposal of mathematical models that can be part of EWO. Artificial brains, integration of artificial intelligence and mathematical programming, are the result of HI's research in disruptive mathematical modeling methodologies for Industry 4.0. And they are the basis of the computational architecture of our proposal. For more information, those interested are invited to watch the video. Artificial brains, artificial intelligence, and mathematical programming integration. This information is part of this proposal. Artificial brains correspond to the scientific foundations, more specifically to the mathematical foundations, which allow multiple mathematical models, algorithms or robots, to be connected, exchanging information between them to obtain a common goal, and acting as holistic intelligence of organizations, or parts of them. Like the human brain, the artificial brain is made up of the following artificial components. Neocortex acts as an organizer of the connectivity of mathematical artificial neurons. Hypothalamus, it is the central processor that coordinates all the models included in an artificial brain, and hippocampus, it is the memory of the brain that stores the history of what is happening in terms of mathematical model runs. It is coordinated by a traditional artificial net. Industrial enterprise-wide optimization. Industrial value chains can be conceived as multiple links that work as the union of two chains, supply and demand. The supply chain is associated with production activities, while the demand is associated with the business. These chains cannot be thought of as mutually exclusive, as the border that could divide is fuzzy. What is clear is that they are complementary and that their union affect all the value chain. HI models mainly support two types of industrial planning activities. SANDOP, sales and operations planning activities that are carried out periodically, usually every month or every week, to coordinate the selling products with production activities. IBP, integrated business planning, activities that are carried out periodically, usually every 6 months or every year, and aim to perform integrated value chain of the organization planning. The solutions offered by HI to the general industrial sector are based on the integration of following groups of solutions. HI DCO, Demand Chain Optimization. HI SCO, Industrial Supply Chain Optimization. HI Bio, Bio-Industrial Supply Chain Optimization, and HI HRA, Human Resources Analytics. In 2006, Jeremy Shapiro published the article Beyond Supply Chain Optimization to Enterprise Optimization, in which he stated, "The recognition that strategic supply chain planning should be integrated into larger business planning exercises will serve to break down barriers to fact-based decision-making. Starting from SCM or supply chain management, focused on production, as a first step in standardized planning." Shapiro envisions what the S&OP, Sales and Operations Planning model, formally is, as the integration of sales and production planning. And finally, it establishes what is now IBP, Integrated Business Planning Model, which involves the financial planning as part of planning. The actual experience has not been as Shapiro envisioned it, but every time we are close to it, with the incorporation of ALM models, assets and liabilities management, as part of supply chain planning. In the paper, Enterprise Profit Optimization, EPO, The Next Wave in Value Creation, Robert Phillips from Manugistics, said, "Integrating pricing actions and supply chain actions, EPO provides companies with the tools required to quickly and effectively achieve real optimization goals." Until the advent of Industry 4.0, S&OP modeling was concentrated on production modeling. Considering as parameters exogenous, the result of models for sales and maintenance. The financial results are obtained from a post-processing, in some cases in Excel books. In the ERA of Industry 4.0, S&OP may be constructed based on 8 groups of solutions or systems: production, energy, maintenance, distribution, sourcing, human resources, financial, and sales and marketing. HI view the systems as groups of equations that must be included in the S&OP mathematical problem depends on many factors, so that there is no revealed truth regarding what the S&OP problem is. Since the equations are defined in a database, the configuration of a problem is limited to selecting from the equation store which are the ones that the modeler wants to consider in the model. Visually, it is easy to see the evolution of the traditional S&OP concept to a modern IBP, that covers, virtually, all the operational functions of an industrial organization. This leads to 2 problems that must be solved from a computational point of view. If traditional approaches are used, a large number of programmers are required to generate all the necessary source code, and to coordinate all the models, and large computational power is necessary to solve the integrated problem. This evolution gives rise to enterprise-wide optimization. Enterprise-wide optimization, the comprehensive and complete view of the value chain, improves competitive advantage, reduces costs and increases profits. Therefore, managers seek to comprehensively optimize the planning and scheduling activities of their value chain, which was originally understood as the coordinated sum of supply chain management, SCM, and demand chain management. Today, AWO has expanded and covers all functional areas of the organization, including financial and human resources chains. There are 4 dimensions to the optimal synchronization of a supply chain, namely: functional associated with the purchase, manufacture, transport and storage of industrial inputs and products; spatial associated with activities through industrial facilities and different forms of markets; hierarchical, associated with the impact of decisions, strategic, tactical and operational; and business. Enterprise integration makes SCM one of the components of a broader view of integrated planning. They respond to the purposes of strategic and tactical planning within the organization. Hierarchical coordination of planning tools. It is traditional to organize decisions hierarchically into strategic, tactical and operational. The operational decisions are divided into the scheduling and advanced optimal control. However, due to the technological progress generated by Industry 4.0, mainly in relation to smart metering systems, nowadays we can talk about a new type of online optimization modeling, Real-time distributed optimization. From the point of view of mathematical modeling, hierarchical levels are intertwined and coordinated through the boundary conditions in time, and common modeling that can be shared. The modeling strategy of HI is that all models of a decision support system can communicate with each other. Under the principle of transitivity of algebraic formulations, models grow in complexity as they descend from the hierarchy of decisions. All models share equations, mainly those related to the physical process. Therefore, they can be made in a continuous modeling process. The models of higher hierarchy will be more aggregated, in order to cover long periods of analysis, of the order of the years. The emphasis of the model should include the interpretation of the economic and technological future, so it is appropriate that they are stochastic optimized. As the models approach real time, the level of detail increases, and the planning period decreases, the most important being the engineering representation of the process. Spatial coordination is related to activities through industrial facilities in various regions and different forms of markets. The decision support systems, DSS, were conceptualized as a set of mathematical models that exchange information between them, working offline. The artificial brains is the evolution of DSS under the Industry 4.0 revolution that is conceptualized as a set of mathematical models that exchange autonomously information between them, working online, using distributed optimization. High Oil AWO meets all the software solutions developed by High, in different areas of application of mathematical optimization models, oriented to planning and to scheduling operations, in different business of the petroleum products supply chain. To ensure optimal decision-making at the level of strategy and tactics, the system must be considered, synchronizing the different links in the chain, in space, function, and time. The management of the complete oil supply chain must be based on the integrated optimization of the different links. It is one of the main research topics worldwide, due to the importance and impact of the products it handles. The support of this type of planning is complex, and therefore turns out to be a perfect field for the application of optimization tools, mathematical programming, in order to support decisions that allow the optimal coordination of the holistic supply chain. Oil enterprise-wide optimization integrates mathematical models for each of the links in the oil supply chain, in such a way to management the planning of the supply chain with a holistic vision. The design of High Oil AWO was the result of work done for a multi-business oil company. The union of models, and their coordination, forms the hypothalamus of an oil enterprise. The current computational power allows to model detailed the supply chain, considering individually all the systems that compose it. This allows to visualize all the existing bottlenecks, and that affect the maximization of economic gains. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. Structured mathematical modeling allows all models to merge around a core of equations that connect them all. Large-scale optimization and artificial brains. One of the fundamental ideas of the artificial brain is the atomization of the system, bottom-up approach, to integrate multiple mathematical models, using the framework of large-scale optimization methodologies, like multi-level Bender's theory, and Lagrangian relaxation. Given the complexity of the real world, which involves mathematical models of all types, linear, nonlinear, discrete, continuous, convex, non-convex, etc., it cannot be thought that with a single methodology, all the problems that make up an artificial brain can be solved. Therefore, it is required to have access to multiple large-scale optimization methodologies, which, using the principles of cross-decomposition, connect all mathematical problems, to perform autonomous distributed optimization in real time. Large-scale optimization technologies rely on linear programming as the basic algorithm. Oil and gas optimization solutions. Below are several optimization solutions, commonly applied in the oil industry. The oil industry includes global processes of exploration, extraction, refining, transportation and marketing of petroleum products. The largest volume products in the industry are fuels, natural gas, fuel oil, and gasoline. However, petroleum is the raw material for many chemicals, including pharmaceuticals, solvents, fertilizers, pesticides, and plastics. The table prepared by IBM Alog presents a general map of problems in the oil and gas sector, which are traditionally associated with optimization problems. These problems are divided hierarchically, according to the length and granularity of the planning period. They are classified as strategic, tactical, and operational. Petroleum refining and petrochemicals. Mathematical models. The table presents an overview map of problems in midstream, which are traditionally associated with optimization problems. The shaded part of the table presents the main problems associated with oil refining. Traditionally, these problems are analyzed independently, and coordinated by connecting the results of independent models for each of them. While this is a valid approach, because it produces near-optimal solutions, but an integrated solution produces the optimal solution, in a large company this difference implies a large loss of profits. Under the modern vision of enterprise-wide optimization, production planning models, of any hierarchy, must integrate multiple functions, or models, and not be limited to sales and production planning. In the case of planning a large refinery, the following group of models, or functions, should be considered. Oil refining. Energy and industrial services. Oil assets maintenance. Sales and distribution. Crude oil sourcing. Human resources, and financial. Oil enterprise-wide optimization integrates mathematical models for each of the links in the oil supply chain, in such a way to management the planning of the supply chain with a holistic vision. The design of High Oil AWO was the result of work done for a multi-business oil company. The union of models, and their coordination, forms the hypothalamus of an oil enterprise. The current computational power allows to model detailed the supply chain, considering individually all the systems that compose it. This allows to visualize all the existing bottlenecks, and that affect the maximization of economic gains. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. Oil refining optimization. Hypothalamus AI considers the production process as a union of two processes. Product transformation, conversion of barley into commercial products, through processing units, and energy transformation, processing of auxiliary industrial services required by process units, and which are consumers, or energy producers, in the service units. To optimize energy efficiency, the first step is to optimize the integrated supply chain, since this is the part of the production process that consumes more economic resources. Hypothalamus AI considers the production process as a union of two processes. Product transformation, conversion of barley into commercial products, through processing units, and energy transformation, processing of auxiliary industrial services required by process units, and which are consumers, or energy producers, in the service units. Hypothalamus AI considers the production process as a union of two processes. Product transformation, conversion of barley into commercial products, through processing units, and energy transformation, processing of auxiliary industrial services required by process units, and which are consumers, or energy producers, in the service units. The image presents an example of a refinery, which is composed of 5 facilities, or process units. A simplified flowsheet of a crude oil refinery is shown in the graph. The process is divided into 3 stages: crude oil management, crude to fuel transformation, and blending operations. The video oil refining optimization, advanced analytics solutions presents High's vision of this problem, and should be considered as a reference for our proposal. Linear optimization model for sales and operations planning, S&OP. High Oil Ref includes a generic model that can serve interchangeably to plan, at the aggregate level, the 2 crude and/or biomass refining processes. The level of aggregation is fundamentally related to the non-linearities associated with this type of process, but not with the level of detail with which it is possible to represent the production processes, which can be spatially detailed in all units used in the production of refined products. High Oil Ref considers the refining process as a union of 2 processes. Product transformation, conversion of crude oil and biomass into refined products, through process units, and energy transformation, processing of auxiliary industrial services required by process units, and which are consumers, and/or energy producers, in so-called service units. The objective of optimization is to determine the production plan that meets the demand for refined products, according to an offer of available crude strips, purchased or to buy, during the planning period. From the point of view of mathematical modeling, High Oil Ref considers two types of process units. Rigid unit considers a unit as a process that is defined based on certain input, raw material, refined final or intermediate products, and that produces refined products in fixed proportions, and flexible unit considers multiple possibilities for production processes in which the proportions of the blending of the products consumed, and the quantities produced, are determined by the model. For flexible units, quality specifications must be introduced as part of the model constraints, so that the volume and/or weight product generated by the model meets these specifications. High Oil Ref includes a multi-technology unit, associated with the multiple ways how the process unit can operate over time. By this way, the model can select which technology, mode of operation, it uses as a decision variable. This possibility implies that in strategic and/or tactical models the process is described based on the amount, or percentage, of time during which each of the available technologies is used. In scheduling models, binary variables are required to describe which technology is used at each instant, or period of the planning horizon. The modeling of the connectivity between production units can be done in an aggregated way, through tanks, or in detail through collectors. This representation is appropriate when it wants to visualize bottlenecks in the flow of products, and when it wants to link the auxiliary service plant with the process plant. Modeling a refinery based on a single type of unit has its drawbacks. A fixed refinery always produces excessive amounts of some finished products, a flexible one generally has too much flexibility compared to a real refinery. That is why the best strategy to model refineries is based on a competition between rigid and flexible units considering costs, demand, capacity, production, profit, and possible expansion of the refinery. However, the units, rigid or flexible, can operate continuously, or in batches. In addition, the flexibility of the unit extends, not only to the different refined products but also to the different raw materials, to the sources of the raw materials or even to any possible combination of them. In this way, the refinery processes can be optimized through a model with a unified mathematical representation, where all types of units, processes, and forms of operation are incorporated. As a byproduct of processes are considered the pollutants of the environment, on which restrictions may be imposed. Multi-period refinery planning mixed nonlinear model. This section is supported in the paper. Refinery production planning, multi-period MINP with nonlinear CDU model. The configuration, like the one shown, it provides information on the major separation, conversion, and blending units, along with the refinery feed streams, product streams, and interconnections between the different units, where the crude is separated into different cuts in the crude distillation unit, CDU. Each cut is sent to a different conversion or treatment unit, reformer, catalytic cracking, or hydrotreatment units, or to product blending. Refineries differ in the number or types of process units they have, depending on the quality of crude oils they process and the product slates. In addition to the configuration, the following information is assumed to be given. Crude oils. The availability of crudes is specified, along with their properties and compositions, usually in the form of crude oil trials. Various processing parameters, property values, and indexes are generated. Refinery units. Capacities of these units, and minimum power requirements. The coefficients required for the yield, and property calculations, are generated from the units, and crude oil information. Product slates. List of products produced by the refinery and their possible constituent streams. The qualities of the product are specified along with requirements, minimum and/or maximum. Demands are specified at the end of each period. Product inventory. Initial inventory of the products at the start of period 1. Changeovers. The variations in crude qualities are sequence dependent. The changeovers are specified in terms of duration and cost. Based on the above information, the objective is to determine the operation that maximizes profit in terms of the following decisions for each period: what crude oil to process, the quantities of these crude oils to process, the sequence of processing them, the rate of processing those crude oils and the processing duration, and the refinery products produced, their quantities, and storage requirement. The mathematical formulation for the multi-period refinery planning model builds on the previous work of Alatas, Grossman, and Pillow Rivera, 2011, and Erderick Dogan and Grossman, 2008. The formulation can be broken into 3 layers. The inner layer is the fractionation index model, phi, which is the nonlinear CDU model. The middle layer is the refinery planning model, which in this work is a linear model. The last layer is the multi-period extension, which is a MIM model. The appeal of the phi model is that it is crude independent. Phi values are characteristics of CDUs, they are readily calculated and updated based on refinery data. It is based on simple nonlinear modeling approach, avoiding more complex ones, calculates cut point temperatures that helps in other calculations and models, and has relatively few equations to add to the planning model. The NLP model for the CDU starts with a mass balance around each unit J, and component I. Every unit yields the top product PD feeding the next unit, and the bottom product PB, which is the product crude cut. There is also a summation equation for each type of stream, over its set of constituent I components. Ti is the output boiling point temperature of component I. The image presents the equations that must be met. The splits of the distributed components are calculated using the phi parameters. For each unit, there are 2 phi values, one for the rectifying section and another for the stripping section. Choice of the correct value is based on the calculated temperature and the component. The rectifying phi, FIR, is used if the temperature is greater than the component boiling temperature, otherwise, the stripping phi, FES, is used. The disjunction represents the phi choice where y is the vector of binary decision variable, gamma is a placeholder for the phi value, TBI is the component boiling point, and TJCRT is the cut point temperature in period T. The component distribution at each unit J is based on the light key LKJ, and heavy key HKJ components for each unit based on the initial and end boiling points relative to each cut. The components lighter than the light key are only obtained in the top product stream, while the ones heavier than the heavy key are only obtained in the bottom product stream. The next model is the refinery planning model. This includes the set of equations for calculating the product yields from each process unit, except the CDU, as well as stream properties calculations, and product blending. Typically, the planning model will include checking the feedstock availability, meeting the product demands and the objective function. However, these constraints and equations are moved to the next layer of the model as part of the extension from single period to multi-period horizon. The throughput of process unit K is calculated using a coefficient multiplied by the feed unit, to obtain the output unit product flow. The capacity requirement of unit K is ensured by using the appropriate constraints. The interconnections between the process units are managed using several splitters and mixers. The crude processing rate is linked to the CDU model. Blending is a mixing unit, but is distinguished by the final product flows, according to the defined constituent flows, and the quality are checked against the product specification, using constraints for the maximum and/or minimum specifications. In this case, the refinery planning model is a linear model. The multi-period layer is based on the approach proposed by Erderick Dogan and Grossman, 2008. The idea is to determine the length of the processing times for each crude oil, and to use traveling salesman constraints, to determine the sequence for processing crude in each period, and identifying the link to break, and connect the sequence to the adjacent periods. The objective is maximizing profit. When there are no sub-cycles in any period, the changeovers are properly accounted for in each period, and any possible crossovers. Otherwise, subtour elimination constraints are added until all sub-cycles are eliminated. Also, Since the duration of the changeovers is relatively modest, the model assumes for simplicity that changeovers cannot cross periods. The extension to this case can be easily implemented. The development of these planning models is broken into two categories. LP models, namely fixed yield and swing cuts, like PIMS, and NLP models, including the aggregate model and fractionation index model. In this case the model is MILP. Case: Crude oil scheduling and refinery planning. This case is based on the document Crude oil scheduling and refinery planning by Lagrangian relaxation. Both crude oil scheduling and refinery planning are formulated as optimization problems, and are integrated into a single full-space MILP. The integrated formulation is constructed based on the overlap between the CDU charging operations and the scheduling level, and the CDU feeding decisions at the planning level. An MILP priority slot-based continuous time crude oil scheduling formulation, and a multi-period discrete time NLP refinery planning formulation are used. A multi-scale framework has been proposed to integrate different time representations. The custom indicates that the most common position, when formulating a mathematical model, is an integral formulation, full space, which brings together in a single formulation all the equations that define the problem. This corresponds to a top-down approach. In this case the model could be called Crude Oil Scheduling and Refinery Planning Model. However, considering the evolution of computational power and algorithms, today in ascending formulation, it is indicated that starts from the atoms, that is, from the basic parts of the problem. This corresponds to a bottom-up approach. The case presented is a good example of this approach, dividing the problem into two formulations, crude oil scheduling model, and refinery planning model. These formulations are integrated to form the holistic model. The mathematical formulation for the full space problem is developed in three stages. Multi-period discrete time formulation for refinery planning, RP, maximizing the total NPV. Priority slot-based continuous time formulation for crude oil scheduling, CS, with multi-period extension, minimizing the total crude purchasing cost, and set of linking variables and constraints of crude oil feedstocks between crude oil scheduling and refinery planning, with the objective maximizing the total NPV minus total crude purchasing cost. The video case, Crude Oil Scheduling and Refinery Planning, presents more details of this problem. Industrial Services Optimization. High oil ISO corresponds to one of the models oriented to the optimization of energy consumption in industrial plants that include large-scale industrial service plants, such as refineries, petrochemicals, etc. These services often include self-generation, cogeneration, and the exchange of energy with the interconnected electricity system. The objective of the model is to minimize the consumption, or cost, of the energy required by the industrial processes, supported by the industrial services plants. The industrial services system is coupled with the production process model to holistically optimize the transformation of crude oil into refined products. This section focuses on industrial services plant optimization. Service plant, place where various industrial operations, related to the auxiliary services demanded by process plants are developed. Auxiliary service, essential services for the operation of any production system, they allow to guarantee the quality and the continuity of the process, and service unit, facilities that make up the service plant, its function transform the different services to adapt them to the requirements of demand for auxiliary services of the process plant. Demand fluctuations are typical of utility or thermoelectric plants in petroleum refineries. Among the major causes are changes in the oil feed properties, multiple operational campaigns, maintenance of process units, interruption of electric energy supply, and cost variations of fuels and electric energy. On the other hand, utility systems are essential for the operational feasibility of refineries. They and must continually adapt their production levels to satisfy such dynamic demand patterns. Therefore, the designs of utility plants tend to present a high level of flexibility, thus allowing multiple operational configurations that satisfy the same demand targets, sometimes with significantly different operating costs. It is important to note that the operational management of services plant, it is a complex process that benefits from the use of optimization technology. The classification of the services demanded by different processes is described in the table. They are water, electrical energy, steam, and fuel. The processes that govern energy exchange and fluid dynamics are nonlinear processes. The optimal point of operation of the units of the service system varies depending on the flow, the temperature, and the pressure handled by the unit. Efficiency is a nonlinear indicator of great importance, with which the amount produced can be related compared to the amount of raw material used. For the management of this indicator, it is necessary to manage an adequate data acquisition system, which ensures the correct measurement of the parameters that facilitate its use. In service plants, we find different types of units that interact and interconnect with other units to transform one service into another service. Different types of service units are used to describe the process, although the diversity of units is clear, and the functionality of each of them, within the modeling they will be considered as a single entity, characterized by the value of the parameters that define it. These parameters refer to input, product, and driver. The table presents the main units that make up the service plant, and their basic functions. Units such as pumps, boilers, accumulation tanks and valves, condensers, manifolds, steam turbines are specified. There are other fundamental elements for the proper functioning of the service plant, such as the measuring units to control the operating conditions of the units, such as pressure gauges, thermometers, water level indicators, flow meters for steam, alarm and control devices, among others. These elements are not handled as entities within the mathematical model that represents the service plant, but they are of great importance, since they make up the data acquisition system, fundamental to the state estimation modeling process. The Video Industrial Services Optimization, Advanced Analytics Solutions presents HI's vision of this problem, and should be considered as a reference for our proposal. Case: Oil Refining and Industrial Services Integrated Optimization in Petrobras. This case is based on the paper Operational Optimization of the Utility System of an Oil Refinery. The Video Oil Refining and Industrial Services Integrated Optimization in Petrobras presents more details of this problem. The Petrobras mathematical model can accurately represent the topology and optimize the operation of the real-world system under different utility demands and abnormal situations in single and multi-period scenarios. The model is currently integrated with the Petrobras plant database and used for the planning of the recap refinery utility system, achieving up to 10.7% reduction cost in static optimization for redesign the configuration of the service plant, and 3 to 5% average savings for dynamic operation of the integrated systems. All this in controlled experiments. The central process of tactical optimization of production and energy management is related to the integration of the two systems through integrated mathematical modeling. Artificial intelligence transforms business sustainability. The use of decision-making artificial intelligence, DMAI, is becoming more common to help companies achieve their carbon emission reduction goals and become more aware of the impact their business operations have on the environment. According to a study conducted jointly by Microsoft and PwC, the use of artificial intelligence can help companies provide valuable information and help them make more informed decisions, leading to better results in their sustainable practices and in their economic results. In this sense, the research reveals that DMAI can improve energy efficiency by analyzing data from sensors and other sources to identify areas where energy consumption can be reduced, optimizing mathematically their operations, and reducing polluting waste. The DMAI is an essential factor for sustainability. It's the key to unlocking knowledge, driving industrial efficiency, and enabling the transformative change we need to address global environmental challenges. Demand response is the name given to the actions that consumers, industrial and residential, can, or should, take to act properly in the new electricity system, which includes actively participating in the marketing. To act as an effective agent, industries must know the structure of the electricity system and market. The diagram presents a typical structure, indicating the relationship of consumers with the physical power grid and with the market. In this structure, two types of agents are displayed: interconnected system operator, ISO, and consumers. ISO, as the name implies, operates the grid, dispatching centralized electrical resources, and it manages markets, creating incentives for demand management. For their part, consumers receive price signals from the market, buy, and/or sell electricity to the market, and consume electricity from the national grid, and/or produces electricity with their smart grid. To participate in demand response, the type of company must be matched with the opportunities provided to companies. In 2007, the North American Electric Reliability Corporation, NERC, published a study in which it analyzes different types of industries, and relates them to the type of services they must offer, considering their industrial processes. However, it should be noted that at that time there was no possibility of considering energy storages, which allow smart grids that can participate in dispatchable demand. It should be noted that, in industrial environments, the possibilities of energy storage can be very different from traditional ones, since there are industrial processes that can store energy as part of the process. Demand response and energy efficiency is a major issue for heavy industry, as it is an opportunity to significantly increase its profits, and to decrease the carbon footprint of its industrial processes, turning the process of maintaining an eco-sustainable into a good business. To achieve optimal planning and scheduling of energy management, 4 major challenges must be faced: accurate modeling of process dynamics and operational flexibility, integration of production management and energy management, optimization at multiple space-time scales, and optimizing decision-making under conditions of uncertainty. These aspects will be discussed later. The model determines the operational configuration of the plant, by minimizing utility costs, and identifies steam losses as well as inefficient units by comparing the optimal solutions with the current operation. The MILP can accurately represent the topology, and optimize the operation of the real-world system, under different utility demands and abnormal situations in single and multi-period scenarios. Those interested in learning more about this topic can watch the video. Energy efficiency, innovation and digital transformation in the heavy industrial sector. An approach based on scientific praxis. Water consumption minimization in industrial complexes. Multi-period refinery planning mixed nonlinear model. Saving and using water in industrial complexes. We can save water in industries by raising awareness among employees, measuring water consumption, optimal water use, waste recycling, installing water-saving equipment, routine pipe checks, etc. Only 3% of the water on Earth is pure and can be used for daily routine. In 1999, between 5 and 10% were consumed for industrial purposes. As the world's population grows, water consumption will also grow. By 2030 it can reach up to 20%, so it is necessary to raise awareness about ways to save water in industries by reducing their consumption. In addition, it will help the company reduce its water bills. Normally, in standard industry, water is used for the cooling of plants and equipment, the cleaning and preparation of products, cooling, and the application of paint and stains to the product. But there are industrial processes, intensive in the use of water, such as the production of shale gas. Wastewater treatment plants. The major aim of wastewater treatment is to remove as much of the suspended solids as possible, before the remaining water, called effluent, is discharged back to the environment. As solid material decays, it uses up oxygen, which is needed by the plants and animals living in the water. Primary treatment removes about 60% of suspended solids from wastewater. This treatment also involves aerating, stirring up, the wastewater, to put oxygen back in. Secondary treatment removes more than 90% of suspended solids. Saving and using water in industrial complexes through economic optimization. Analysis of water networks whose application can help to reduce the consumption of fresh water, first use, reduce wastewater generation, reduce water costs, determine the investment needed to achieve a specific goal. Use of advanced decision-making, artificial intelligence to identify the best opportunity to reuse of currents, regeneration, and treatment. In addition to the benefit of saving this scarce and valuable natural resource for the humanity. Software of Instituto Mexicano del Petróleo, IMP, for water consumption minimization in gas complexes and refineries. AUGURT is the IMP software for the minimization of water consumption in gas complexes and refineries. His goals are: decrease water consumption, cooling systems, steam generation system, other industrial services, and efficient water management. Those interested in learning more about this topic can watch the video. Water consumption minimization in industrial complexes. Tactical maintenance optimization. Large industrial assets maintenance optimization. The optimization of the maintenance planning of industrial facilities is a daily problem for all productive sectors, as it involves the coordination of production activities, which use this infrastructure as the main resource, and the maintenance activities that are required for this infrastructure to function effectively. The model aims to schedule maintenance in such a way as to minimize costs, or maximize revenues, resulting from the simultaneous coordination of production activities and maintenance activities. Optimization models, mathematical programming, are used to map maintenance activities and production activities, which are solved using high-performance solvers. Optimization is carried out considering, among others, the following aspects: the demands met by the production chain, maintenance costs, the usefulness of production, the resources used in maintenance processes and their availability. The constraints included in the models simulate each production line in a customized way. The mathematical models required to carry out this work can be classified into two types: models for optimization of maintenance activities, and models to support the general maintenance management. The maintenance of industrial plants, associated with production plants, or process units, that make up the large industrial facilities. These processes may involve shutdown of plants/units, or duration of production leading to a decrease in the productivity of the industrial asset. Example: maintenance in an electricity generating company. Objective: determine the optimal policies for maintaining the infrastructure of an electricity generating company. Results: allocate the use of maintenance resources, labor, equipment, tools, etc., minimize maintenance impact. Decisions on dates for maintenance. Minimize total costs, direct costs plus loss of profit, and maximize economic benefits. Large industrial plants often have electricity generators the size of a commercial plant. Equipment maintenance optimization. Below are three groups of mathematical models that are required to optimize the maintenance of industrial assets. Maintenance of machines, or equipment, or vehicles, associated with the maintenance of multiple assets that operate simultaneously in an industrial environment, which require maintenance activities as the productive life is consumed between maintenance. These maintenances are scheduled at the team level, each of them independently. Inventory management of spare parts and spare parts. Normally, to ensure the timely maintenance of spare parts, it is necessary to maintain inventories of parts and spare parts, which are associated with working capital that generate high financial costs. Scheduling of activities in industrial workshops. Industrial workshops are an integral part of factories and have the function of ensuring maintenance activities. Equipment maintenance model. Objective: determine the optimal policies for the operation of the assets, taking as a reference that they are composed of multi-level fault structures, each of them with its own probabilistic characteristics of failures of its components. Decisions: determine the optimal consumption of the asset before its next maintenance. Determine the maintenance actions that need to be carried out once the decision has been made to stop the asset to maintain it. Programming activities in workshops. Activity scheduling model in truck workshops. Objective: schedule the activities to be carried out in the workshops, allocate maintenance resources, according to the demand for services, the duration and sequence of these activities, and the availability of resources. Results: detailed scheduling of maintenance activities. SAND-OP and ALM, integration of production, finance, and taxation models. Enterprise risk management, ERM. The idea behind ERM is that an organization's, while it can't eliminate risks, it can manage the risk. ERM is a scientific approach to shaping risk, which is based on trading research methods such as applied probability and statistics, stochastic simulation, and investment portfolio optimization. ERM is a rigorous approach to quantifying and managing risks, from all sources, that threaten the achievement of an organization's strategic objectives. In addition, ERM identifies those risks that correspond to opportunities, which allow competitive advantages to be exploited. Its goal is to increase the wealth of owners. Stavros Zenios, former ex-director of the Hermes Center of Excellence on Computational Finance and Economics, University of Cyprus, defines ERM as the strategy that aligns the firm's businesses with the risk factors of its environment in the pursuit of strategic objectives. ERM is based on conceptual structure, organizational approaches, and analytical tools that integrate market, credit, liquidity, operational, and business risks to achieve the organization's objectives. Assets and Liabilities Management, ALM. ALM allows you to align the risks of the environment, which are reflected in the balance sheet, and in the profit and loss account, on both the asset and liability sides. ALM correlates all of an organization's risks, so that the calculation of the total risk exposure faced by the organization is not reduced or increased, as occurs when risk correlation structures are ignored. And ALM is defined as the management of assets and liabilities, supported by stochastic optimization techniques, to obtain an adequate economic return, protecting the company from extreme risks. This is achieved through the structuring of synthetic generation processes of probabilistic scenarios, which are considered in the algorithmic procedures, typical of multi-stage stochastic optimization. Optimization modeling, production, finance, and taxation. The integration of mathematical programming models, better known as optimization, is since mathematical programming is a standard for the modeling of physical systems and business processes. This is because, joining mathematical programming models, algebraic models, generates a new model, or a variation of an existing model, of mathematical programming. In the case of integration of production and finance, there are originally two models, S&OP and ALM. These models can be summed, resulting in a mathematical model containing the constraints of the two models, forming the S&OP ALM model. The user will have three models, the original ones and the integrated model. The integration process can be conceived as the S&OP model that generates results, production and sales, which must be transformed into financial results, in the ALM model, in such a way that the financial statements of the organization are produced, the control of which is the true objective of a private company. The traditional thing is to coordinate the two models, in such a way that the productive model feeds the financial model. This process has no feedback, and therefore the financial model can be a workbook in Excel. The modern vision is to integrate the two models into a single model, which has significant advantages. It's a feedback model between the two systems. The field of control is expanded, as it is possible to introduce financial constraints into the production model, for example, cash flow constraints. Financial variables can be entered as part of the target function, e.g., the value of the firm at the end of the planning horizon, and achieve optimal solutions, which are not obtained with the coordination of models. From a functional point of view, the integration of the models implies the direct involvement of the board of directors in the planning of the company. As a substantial improvement of the decision-making process, linking the financial model with the supply chain model allows you to optimize comprehensive modeling of global supply chains, tax management, dividends, capital repatriations, payment and prepayment of liabilities, etc., capital structure, transfer pricing, and corporate financial risk analysis. Due to the difference between different countries' tax policies, tariff regimes, exchange control policies, and export promotion policies, an integrated model is necessary for the proper optimization of global supply chains. For example, it is the only way to simultaneously determine, Optimally, transfer pricing and amounts to be transferred between subsidiaries of a global corporation. This is related to the management of Incoterms, which determine the flow of money. For example, the FOB transfer will leave the money with the exporter, and the CIF with the importer. In a global supply chain, product flows and money flows between different regions must be determined. Those interested in learning more about this topic can watch the video. Enterprise-wide optimization. Production, finance and fiscal integration. Case, transfer pricing optimization. Global supply chains operate in multiple countries, or regions. The operations in each country are independent, but the planning of the chain must be holistic, as it belongs to a single organization. This involves having individual mathematical models for each region, which are integrated into one, to holistically visualize the global chain. It is common to transfer products between regions, to capture the competitive advantages of each country. On the other hand, there are flows of money to exporting countries. It should be noted, however, that the goal of the parent company is not to maximize profits in the countries, but the profits of the corporation, and presumably, to place the money where it is most convenient. Holistic planning should consider after-tax earnings, including taxes on bank money flows. This involves considering, among several, tariff regimes, Incoterms, exchange control policies, export promotion policies, free trade agreements, lay labor law, currency risks, and the political risks of each country. The case concerns the hypothetical company Beer Express, which operates in 5 LATAM countries, 6 industrial plants, 15 distribution centers, 15 consumption zones, 25 packaging lines, and 28 end products. The case uses realistic data, coming from real cases, adjusted with financial data. The goal is to use an integrated production finance model to determine optimal transfer pricing, defined as those that maximize corporate profit after taxes. The table presents the income statements for each country, which together make up the aggregate income statement of the corporation. The table presents the summary of the corporate profit distributed by country. The comparison is made between two mathematical models, one with fixed transfer prices, exogenous to the model, and the other with endogenously optimized transfer prices. Those interested in learning more about this topic can watch the video. Transfer pricing optimization. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.